figure, on which of the following intervals is the first derivative greater than 0 and the second derivative less than 0? What would cause a first derivative to be greater than 0?
The function is
increasing, right? So we're talking here for the first part. And when is the second derivative less than 0? What does that look like? Concave down, right? So this part's concave up, so that's the concave down part. So the overlap of that would be from B to C. Any questions about that one? Today we're going to be talking about how to find the area between two curves. Without me teaching, you probably could have figured this out. The first part of it, anyway. Very common AP problem is asking to find the area between two curves. So you have f of x and g of x. F of x is on the top, g of x is on the bottom. Then to find the area, you would do the integral from the intersection of those two graphs to the other intersection of those two graphs. Of the top function minus the bottom function. Would you all agree that would give you the area? Because it would, top minus bottom would give you the distance between, and then you add up all those distances in between, which will give you area.
Why wouldn't you add them?
Adding those two functions together would create a new function, not give you the area in between. So let's talk about first distance. How would you find this distance here? And how'd you get that? Added what?
Added 3.
Which is 3 minus negative 4. You subtracted.
There's 2.
Yeah, well, that's all it is. That's fine. That part, you can argue 3 or 2 all day long. That's not important. But the big deal is, if you are in your head changing the sign of that negative, which is subtraction, right? If you want a standardized way to do that, because what if it was up here? So subtraction always gets you that distance in between. And then we're going to take all of those little distances in between and the little dx width, right, the little width, essentially we're doing, again, a bunch of rectangles. We're going to take all of those rectangles and add them up, and that's what an integral does. Remember, it's a sum of all of the little rectangles from A to B. Any questions about that?
Well, if you don't have an intersection, right? That's A to B.
Right. So
you don't have the intersection.
Let's see.
Okay.
So A to B on that one would be negative 2 to 2, right?
Yeah, it appears so. Yeah, on that one it would be negative 2 to 2. So here is this example is f of x is 2 cosine of pi x over 4, and g of x is x squared minus 4. As Trent pointed out, the intersections there fall at x equals negative 2 and x equals positive 2. So this area would be represented by the integral from negative 2 to 2 of 2 cosine of pi x over 4 minus x squared minus 4. One thing to be careful about that students forget a lot, make sure that is in parentheses. You need to subtract the whole x squared minus 4. So that integral would give you the area between those two curves. Now, as you can imagine, the biggest challenge in this is going to be finding two things. One, which curve's on top, and 2, what are the intersections? If you can figure those two things out, this is not a difficult calculation. But those will be the two things we'll have to figure out to find the area between two curves. which curve's on top, and where the intersection is.
The top curve is just one positive one. Or
Right. Now, again, you're going to have to figure out which one is more positive in the interval that you're looking for. So we'll look at some examples. So this is the first one. And you notice it has to be specific because there's a lot of times that functions may or may not intersect. So this one says, find the area of the region between the graphs of f of x and g of x in the first quadrant. Right. So some of these will be non-calculator. You will have to be able to graph some basic functions without a calculator. Not all functions, right? If they get complex, we're going to pick up a calculator. But do you all know what the graph of x cubed looks like? Do you all know what the graph of y equals x looks like? It actually turns out that we're talking about a very small area, aren't we? We're in the first quadrant, and it says the area of the region between those two graphs in the first quadrant. So we're talking about this little tiny area right there. Is what I want to find. If you were using a calculator to even see that, you'd have to zoom in. So, what do I need to know? Two things I need to know. I need to know the endpoints, where those two graphs intersect. Well, one is probably something you could just see. 0. So I know this is the integral from 0 to something. Well, if I am doing this by hand, how would I find that other intersection? I set them equal to each other. So when does x cubed equal x? 1, you might just be able to see that as well. If you did have to solve this, which I know is probably not something you would have to do, but if you did have to, it would be some factoring. And you get plus or minus 1, but we don't really care about the negative 1 because that's not where the picture, that's not where the question told us to look. So we're going to integrate from 0 to 1. What is the top curve? X. Good. Everyone see that? And what is the bottom curve? As you can tell, this one is probably a non-calculator problem. A lot of these will be calculator, but this one's probably a non-calculator problem. So, how do I do an integral? Good. Anti-differentiate. From 0 to 1. I plug in 1, I get 1/2 minus 1/4. If I plug in 0, I get 0. So, negative 1, no, positive 1/4. So the area between those two curves is 1/4 square units, whatever units are. Does it make sense for that to be a fairly small number? Yeah, it's a little area. Any questions about this one? Okay, try this one. Try this one without a calculator. This would be another good non-calculator problem. Do what? Really? Huh. Almost.
Oh, it goes opposite.
Almost. Whichever one's on top needs to go first. So top minus bottom. So you'll have to draw a picture to figure that out. So this one, X was on top.
Oh.
So that's why I drew the picture. Otherwise, I wouldn't need the picture as much. Gotta visualize that picture and see which one is on top.
But it's not right, you know,
And that one's different than this one.
yeah, no, that's what I draw, that one. But I just not draw it right. It doesn't look like an intersection.
Yeah, I have like 2 intersections. Oh.
Then I didn't draw it right.
Up to.
Oh, it's hard.
Just be right here. If you shoot. I would rearrange it to be negative x squared plus 2. See how much easier it is to tell just with this. Wasn't a lot of work, but it really helps your brain out. Does mine too. Okay, so if you heard my side conversation up over there, for transformation purposes, it's good for you to think of this being negative x squared plus 2. Some of you might have seen that in your head, others of you might need to put that on paper. So I'm going to draw a quick sketch. It doesn't have to be, we're not grading for perfect sketches, but just something to let you know what this looks like. Thank you. Any questions so far? I can now tell from that which curve is on top. Got 2 minus x squared minus negative x so I do the top minus the bottom. What else do I need to know to be able to finish this? The intersections. Remember, I'm trying to find the area enclosed. So I'm looking for that area right there. So I'm going to set 2 minus x squared equal to negative x. Get 0 on one side. Luckily, that's factorable, which makes my life easier. Again, how you can tell that this is a non-calculator problem compared to one that may be a calculator problem. Negative 1 to 2. Where would see that?
Can you do it the other way around? Like put the x on the other side.
Yeah. Then you end up with a negative leading coefficient though. And then you probably want to divide that out. That's why I went to the right to make that x squared positive. But I'm not saying no, that it can't be done.
No, that makes it
I had it the other way, just factored.
Factored, yeah, perfect. I am going to rewrite just a little bit. You don't have to do this, but nope. Let's try that again. Sounds better. Questions so far?
Can you rewrite it that way?
Which way?
Like how you did? Because it's the first function minus the second function. Can you, like, combine them like you did?
You can, but if it hurts your
Well,
feelings, you don't have to.
I didn't know.
Yeah, as long as I don't change this expression. Because
Okay.
I've already done the math there.
Okay, I just wasn't sure if we could.
Yes, you can. But again, I don't know, sometimes you'll have to make integration easier. Well, I don't know, have to. Have to is a strong word. Want to make your, if you have like terms, combining like terms to simplify your life. -8/3. So far, so good. Is that what y'all are getting as well?
I got a second one right here. Yes. So, yeah, I got -3.
The -1 plugged in gives you a -1. Because -1 cubed is still -1. Change all those signs. Works out really nice because -8/3 minus 1/3 is -9/3. Which I think is nice. Let's think about that. 2, 6, 7, 8. So -9/3 is -3. Right. So I get 5 minus 1/2, 4.5. You can either write it as 4.5 or you can write it as 9/2. Okay, let's do this one. Another one without a calculator. I will do a calculator example, I promise. Find the area of the region in the first quadrant that is bounded above by the square root of x and below by the x-axis and the line y equals x minus 2. Is that background hard to read? I'll change that for my next class. They always look different on your computer screen than they do. What's the first thing I'm going to do? Graph it. Do I know how to graph those two things? I hope so. You'll notice those 12 functions you learned last year that your pre-cal teachers made you memorize. They're the ones that AP Cal keeps pulling from, that they expect you to be able to graph by hand. That's how your pre-cal teachers made you learn those. X minus 2. So this is 2. We'll save some time later. Now, I'm going to go back and read this question really carefully. Which region am I talking about?
Part above the wall.
That, right? If I integrate from 0 to that intersection, and I do the square root of x minus x minus 2, what area would that give me? That little triangle as well, right? I'm going to have a couple of options. Good, you could do that whole area and then subtract the triangle, right? It's an option. I'm going to show you another option, but don't forget you could use that. You could definitely do the whole area and then subtract the triangle. But we need to learn a new skill, and that is splitting this into two integrals. This would be the integral from 0 to 2 of the square root of x, right? Minus 0 if you really want to write that right. But the bottom curve here is just 0, so it just gives you a normal integral. So I'm going to do the integral from 0 to 2 of the square root of x plus to get that black area, I'm going to do the integral from 2 to something. We'll figure that out momentarily. Of the top curve, which is minus the bottom curve, which is x minus 2. Notice I put the x minus 2 in parentheses. Make sure you don't forget to do that. I do need to go find that intersection. So, find the intersection. I'm going to set the square root of x equal to x minus 2. This one's a fun one. I have to square both sides. How do you square x minus 2?
Multiply it by x.
Good. Don't do x squared minus 4. You will be wrong every time. Don't do that. Common math mistake. Subtract the x. Luckily, this factors nicely. Now, obviously, which one of those is this point? 4. Just out of curiosity, where in the world are they even getting the 1? Why is the 1 even involved? When you squared, you lost that it was the positive, right? So it's giving you that weird intersection right there that is completely meaningless to us. But that's what it's giving. All right. So I get x to the 3 halves times 2 thirds. Remember, if this is some kind of open response question, you can't leave your answers in unsimplified form. You do have to plug in the numbers, but you can't leave your answers in unsimplified form. So I'm going to plug in 2. So I get 2 thirds times 2 to the 3 halves minus 0. Talk about that in a second. Plus, I'm going to plug in 4. Then I'm going to plug in 2. It turns out pretty nice. It looked like it was going to be really bad because of that 2 to the 3 halves. But what happened to that 2 thirds, 2 to the 3 halves? It's going to cancel anyway, so you see why I didn't waste my time figuring out what that value was. Now let's talk about 3 halves. What is a 3 halves power? It's square root cubed, and I would root first because it makes your numbers smaller. What's the square root of 4? What's 2 cubed? So it's 2 thirds times 8 minus 16 times a half, which is 8, plus 8. Plus, I do need to distribute the negative. 2 minus 4. I'm checking my math there. 8's cancel. And so I get 16 thirds minus 2, which is 6/10. Some yucky arithmetic there. How are we doing with area between two curves? This is a common open response problem as well. So there's a nice one today. Okay. We're going to pick up the calculator. First time. Okay, this one asks us to find the area of the region bounded by those two equations. What are we talking about if we talk about the area bounded by those two equations? And I do have it graphed up here, but you will want to graph this on your calculator as well. That one? Good. We actually have two separate areas we're talking about here, don't we? Can we just do one integral to get this? What's the problem? They switch, right? So I've got to do two different integrals. So I need the integral of, this one is the cubic, x cubed plus 2x squared minus 3x, plus the integral from here to here of 3x minus x cubed plus 2x squared dx. Now you need to learn a calculator trick on this one. I've talked about it before, but here's where it becomes really important. If you will, go to your calculator and find this intersection for me. Calculator skill becomes important because, as you know, we need it to be accurate, right? What'd you get? Exactly. Oh. Is the other one exact? That must be the next one. It's more complicated. Do what? Oh, it's 0. And then 0 to 1. We could have done that one by hand. Because it has an x you can factor out. I was thinking of the next one. Sorry, this was probably another by hand problem. Sorry about that. My bad.
So, like, if it is one non-calculator parts,
If it were non-calculator, sorry. There they are. Really doable. I just missed it. Sorry. I'm thinking too far ahead. Anyway, any questions about that one? We do need two separate integrals though on that one. Anti-differentiate. Because of time, I feel like you could do that anti-differentiation by hand. Because of time, plug that in your calculator so we can get on to another example. If we were to do this by hand, you would get a fraction value for that. So, any questions about that one? There we go. This is a calculator problem. That's all right. We needed to go fast through that one anyway. So, use a calculator to find the area enclosed by 2 cosine of x and x squared minus 1. So graph those. Do what?
I'm guessing it has to do with pi, but it's just a mess.
Okay. These intersections are not pretty. I know this one. I'm pretty sure. So we are going to do the area enclosed. Which one's the top function? 2 cosine of x minus x squared minus 1. Go find that first intersection. Back to where we were when I...
Negative
1.26.
Go to your home screen.
The other one's the same thing.
Type x, store, and type a letter. I usually use A. I've heard people say you might not want to do that because it might mess with your quad 3. Like if you use quad 3, it would change your A, and you might not realize your A changed. To me, I figure I'm not going to use quad 3 in the middle of this problem anyway, so. But you can store it as any letter you want. Don't use X or Y. But other than that, any letter is good. It automatically stores as X, but we're going to go find the other one, and your X will change. So, store, you type, does everyone know how to do that? X, store button, alpha A. And then anytime you type A, so on my paper, if this were an open response problem, I'm going to label this A, and I'm going to say A is approximately, and what did you say A was?
Negative 1.265.
Negative 1.265.
Yeah, that's the same.
B. And so you could store them both, or you could do negative A, or you could do A to negative A, but to me that might weird your brain out, so I'm just going to do this, and in my calculator, I'm going to type that. Exactly like that in my calculator. I'm going to write it on my paper that way for the AP reader to see that they know I'm using these values, but I'm using a stored values. Type all that in my calculator, and I get, make sure you do the parentheses around the x squared minus 1.
1.995.
Have you kind of picked up what? Okay, so,
Where did you store it at?
so you get the intersection. Did you get the intersection? So you have to go to the graph and find the intersection and store the left-hand intersection as A and store the right-hand intersection as B. So find the intersection, leave your cursor there, go store it. So I'm going to call that B. And then go back and find the other one, store it as A. Any questions on this one? Abby, did you catch up with the whole top minus bottom thing? Okay, so to find the area between two curves, you do the top curve, which is 2 cosine of x, minus the bottom curve, and integrate from intersection to intersection. Okay, so if I were to want to find the area enclosed by these two graphs, without me teaching you anything new, what would you have to do? Be pretty nasty, I'll tell you that. So if I start looking here, from here to here, here to here, what's the top and bottom? This thing, right? I'd have to solve for y, and I'd have a top and a bottom from that, right? And I'd have to integrate from here to here. Right? From there to there. That same curve minus itself, but the positive one and the negative one. And then I'd have to integrate from here to here. Right? I'm not saying it's horrible, but it's not particularly pretty either. But what if we thought outside the box? I know x is normally x and y is normally y, but could I just kind of turn this graph around a little and pretend y is x? Turn your head this way.
Rotate the graph.
Yeah. If you do that, isn't there a 1 on top the whole time?
Yes.
We call it the right-hand function, right? You'll see it? So, creative thinking. We could do a dy instead of a dx. We're going to turn our brain this way, and we're going to make our cuts this way. Okay. Essentially, x is y, and y is x. And right would be the top, and left would be the bottom. Essentially, I am truly just turning my brain to make x and y switch. Now, to do that, I have to have the functions be functions of y, right? So that's the first thing I'm going to do. Now, this one is already a function of y. X equals, normally it's y equals, this one's already x equals. Would it take much work to get this one to be x equals? In fact, it would take less work to get this one to be x equals than it would to get that one to be y equals. Y cubed would equal x. So now we have two functions. They accept their y instead of x. So I cubed both, or cube. Thanks. I knew that was, I'm confused with it.
So I get that we can't have different have y equals x and x equals y because that's just to one degree. Are we just making the x cubed because we're lazy the other one? Okay, so either way it could work.
It could. Now, if we did the other one, we talked about if we did the other one, it would require two separate integrals. Because you'd have to do this piece and that piece. So it would be kind of, yeah, definitely doable. Now, I'm not saying we can't. We're just thinking outside the
And we
box.
end up with the same answer.
We end up with the same answer either way. So we're being clever. So, normally we do top minus bottom. Well, what's on top? The cube root, because it's on the right. So if we were to turn this graph, it would be the top function. So the cube root is the right-hand function minus the left-hand function. And now we're dy, because all our little rectangle widths are y widths, right? Where are we going to integrate from and to? there to there, right? Which values do I care about this time on the intersections?
Y values.
Y values. Why the Y values?
Because everything else is black.
Because I want to go from here to here, right? From bottom to top. In this case, those are both Y values. So I want to find those intersections. Let's see if that's easy by hand or not. Probably not. That's pretty yucky by hand. So go find those intersections in the calculator. Can you still use the store button? You would type Y store as A and Y store as B.
But you put them in like
Or actually, you do
When we put it in,
Y1 of X. So let me show you that. No, you can find the intersections with, you have to find the intersection. Well, you can do it either way. If you do it with X equals, then you wouldn't have to use the Y. So
how do you type that
pretty flexible. I'll show you both ways. That's a good point. We wouldn't have to use Y. Okay. Yeah, it is. It's like topsy-turvy world. So in Y1, two options. Abby kind of changed my plan here. One option is just to leave it as your Y values instead of your X values. And then when you find the intersections, the X would be the Y. That's one option. The cube root, so math, cube root, and I've got to type X here. And X squared, what was it, minus 2? So one option is to get your calculator to flip it. So everyone see that? Have your calculator flip it. Now the intersections that I find will be the Y values already. So that's one option. Actually, that's probably the better option.
It says graph backwards for the cube root. That it's y squared minus 2. That's why I was asking you that. Like the cube root, if you flip it on the side, it doesn't look the same as that original graph. It looks backwards.
But I just want to find the intersections.
Well,
Of that Y squared minus 2 equals the cube root of Y, right? That's what I want to find. Because I just want to solve that equation graphically. So, second trace, 5, enter, and I get -1. No need to store that. And I get 1 point, that I need to store, don't I? I'm going to store that as B. Is that what everyone got?
What?
The 1.7.
Yeah.
So I'm going to go from -1 to 1.7. Right. So get that value. On the bottom, I want to talk a little bit about whether you would integrate top to bottom or left to right, which one would be easier. So if you look at those bottom pictures, far bottom left, what would be easier? What's easiest on that one? Top to bottom, right? There's clearly a top, there's clearly a bottom. Top to bottom would be easiest. This one?
Wait,
I'd go top to bottom because that's what I'm used to, and there's no reason not to, right?
Even though it's X
Cube root. But either way, though, you could do, on this one, would everyone agree? Either way would work great, whichever way your brain prefers. What about this one? Right to left. If you did top to bottom, you'd have to do two integrals. You'd have to find that intersection. On some AP problems, they may make it very difficult to do that. So you will need to know that you could go right to left on that one. Don't even try that one top to bottom. You have to solve for y. Good luck with that. So this one is a right to left, no question about it. Top to bottom. Do what? You can. Yes, and as long as you notice stuff like that, you can do it however you want. But if you're just using a curve, you would go right to left. So how do y'all feel about area?
It's just
It's not
hard.
not too terrible.
Yeah, it's just
Different.
Okay, let me really quick, since we have time, I do want to go back and show you, if you wanted to graph this using your x's, how you would do that. It's too far. Oh. Oh, by the way, your tests are graded. They will be on Edline sometime today.